Okay, welcome to this video. In this lecture, we're going to learn about some different theorems and properties that involve differentiable functions. So let's get started here. And our first theorem shouldn't be unfamiliar. It says if you have a function that is differentiable at a point and the function assumes a max or a min at that point, then the derivative actually has to be equal to 0. So the derivative at a max or a min, assuming your function is differentiable there, has to be equal to 0. So I've written here the setup, the hypothesis, and the claim. So suppose f is some function defined on an open interval ab, and at some point in the domain, f assumes a max or a min, and f is differentiable at that point. The claim is that f prime of x naught is equal to 0. So let's go ahead and draw a sketch so we can get an idea of what we could be talking about here. I'm just going to assume that f has a max at x naught. So it could be like this, or we could have the graph of f flat and then scrolling down. So it could be like that, okay? And it could be that your function does something like that, but perhaps our interval of domain is, is restricted. We'd have a situation like this. Now, a key thing, in order for us to prove that f prime of x naught is equal to 0, a key thing for us to remember is to recall the definition of the derivative. So when we say that f prime of x naught exists, this means that the limit as x approaches x naught of f of x minus f of x naught divided by x minus x naught, this limit exists and is some real number. So let's say it's equal to L for some real number L, okay? Now, if we look at our picture here, let me actually just want to make sure that I am not receiving any of those notifications. But so I'm going to take my definition here and move it up so we can refer to our definition and look at our picture. This is going to tell us how to prove this. Remember, we're trying to prove that the derivative has to be equal to 0. Okay, where our function attains a max. Now, if I look at f of x minus f of x naught, when x is near x naught, so say x is over here or x is over here, f of x is going to be less than or equal to x naught. Right, so in this case, for the x's that are near x naught, f of x is equal to x naught. And in the picture I've drawn here, when x is near x naught, f of x is less than x naught, right? So I can say x near x naught implies f of x is less than or equal to f of x naught. And that means that f of x minus f of x naught is going to be less than or equal to 0, right? So what's going to happen when I'm looking at this difference quotient is my numerator will always be less than or equal to 0 since f has a max at x naught, but my denominator could be positive and it could be negative. When will it be positive? It'll be positive if x is larger than x naught, if x is to the right. And it'll be negative if x is to the left. Now, if we're saying that the limit as x approaches x naught is equal to L, that means that the limit exists whether you're approaching from the left or whether your values x are approaching from the right. So that means whatever this limit is, it is the limit of a negative number divided by either a positive number, and it's also the limit of some negative numbers divided by some negative numbers, right? The only real number that could be the limit of positive and negative numbers would be 0. So that's the idea for the proof. So let's go for our proof, and we'll say, first of all, without loss of generality, we may assume that f attains a max at x naught. Now, we're trying to prove that f of x naught is equal to 0, and we could do a proof by contradiction. Suppose f of x naught is not equal to 0, right? Or we don't have to do proof by contradiction. We can just look at this difference quotient and show that it converges to a real number. Sometimes it's a positive, the difference quotients are positive, sometimes they're negative. So the only limit you could have would be 0. Okay? Now, notice that f prime of x naught is going to be the limit as x approaches x naught of f of x minus f of x naught divided by x minus x naught. Since f of x minus f of x naught is less than or equal to 0 when x is near x naught, the difference quotient f of x minus f of x naught over x minus x naught is less than 0, less than or equal to 0 if x is less than x naught, and it is, oh, wait, let me switch it around. If x is less than x naught, then we're taking a negative number and dividing by a negative number, so we'll have a positive number, right? If x is less than x naught, and we'll have a negative number if x is greater than x naught. So f prime of x naught must be equal to 0. Of both positive and negative numbers must be equal to 0. And, we could justify this last line because this is the crux of the proof. We could justify that using a proof by contradiction if we wanted to, right? The idea being, suppose your f prime is positive, then you get a contradiction because what does it mean for the limit to be a positive number? Well, for every epsilon greater than 0, there exists a delta such that points within delta units are mapped to within epsilon units. Let your epsilon be half of the distance between f prime of x naught and 0, right? So if this is your epsilon, then you can say, hey, if I get close enough to x naught, all of my values of the difference quotient should be within epsilon units of my limit. But I'll always have some values over here, negative, and I'll always have some values positive, and you get a contradiction, right? Now, let me go back and just address one more point. We started off our proof by saying, without loss of generality, we can assume that f attains a max. How do we take into account the case, or how do we quickly give a proof if f attains a min at x naught? Okay? So, because oftentimes we'll say, oh, without loss of generality, but maybe, we need to do a little explaining. In this case, let me show you how to go from the case where your function is attaining a max at x naught to the case where your function attains a min. Okay, so side notes. We'll just call this a side note. Suppose f attains a min at x naught. Then our graph wouldn't look like this. Our graph would look like, right, it would look like, maybe it would look something like that, right? So what could we do? Well, look at the relationship between these two. This makes us think, just consider minus f, right? So f attains a min at a point, if and only if, minus f attains a max, right? So we'll say, consider, in this case, consider, say, g of x defined to be equal to minus f of x. Then g attains a max. G satisfies all the hypotheses. and G attains a max at x naught. So G prime of x naught has to be equal to 0. But what is G prime of x naught? Well, it's nothing but minus f prime of x naught, right? So f prime of x naught is equal to 0, too. Okay? So in this instance, I'm just taking a moment to show how easy it is to get both cases, right? Once you've proved the claim for f attaining a max, you can easily get the claim for f attaining a min by considering -1 times the original function. Okay. All right. So well done. We're actually going to use that theorem to prove our next theorem. This is an important theorem, clearly. It has a name. It's called Rolle's theorem. And Rolle's theorem is pretty nice. Let's briefly go over it. Now we're saying, suppose you have a function and you know that your function is differentiable on the interval and continuous on the endpoints, at the endpoints. So the last theorem just said, hey, suppose your function is differentiable at that point. Now we're saying, suppose you're considering a function and the function is differentiable on the entire, right? Function is differentiable on that entire open interval. Suppose further that f of a is equal to f of b. So there's no net change in the function, right? F of a is exactly the same as f of b. The claim is that there has to be a point in your domain where f prime is equal to 0. Okay? So let's look geometrically at what this is claiming. What we're saying is that, or Rolle's theorem is saying, if you have a function that's differentiable and continuous, then if f of a is equal to f of b, so there's no net change, right? The net change is the f of b minus f of a. So there's no net change. Then there has to be a point where your derivative is equal to 0 as well. So a way to think about this is if you think about your, maybe you're driving in a car and you're thinking about your function is distance, or how far you travel from, your driveway. It's not the best function because that's not necessarily a function that's differentiable, because you could be in traffic and you're starting and stopping suddenly. But just go with me for the analogy. Now, if I start at my driveway, so I start off 0 feet from my driveway, and I, walk around, or, I'm in my car and I drive around, and then I end up right back at my driveway. At some point, I had to have stopped. That's the idea, right? So, at some point, I had to have stopped and gone in reverse to come back towards my house, if you can think of it like that, right? So, and we'll get into this later, but if you think of the derivative being positive, meaning you're increasing, and the derivative of the function being negative, meaning you're decreasing, then your derivative equals 0 means you're neither increasing nor decreasing, right? So it's like you kind of have no momentum either going or coming, right, in either direction. So it's like, okay, you leave your driveway, you walk around, at some point you have to stop and change direction and come back home. And if you never stopped, then you're not going to end up in exactly the same place that you started off in. Okay. So again, broad, far-reaching analogy here. But let's go ahead and prove it. And the way we prove it is by actually using the extreme value theorem. So the proof is going to involve the extreme value theorem. And I just want to remind you of the extreme value theorem. So let's take a moment and recall the extreme value theorem. And I'm going to I'll have a lecture where I review the extreme value theorem, the mean value theorem, the intermediate value theorem, all of these value theorems that are important in analysis. We'll kind of bring them all together in one lecture and review them to kind of compare and contrast them to each other. But recall the extreme value theorem. It basically says if you have a function that is continuous, so say on some compact domain, then f attains its extrema. So extrema meaning the global max and the global min. So in other words, why are these extreme? They're extreme because it's like the highest and the lowest values that f attains. So what's our definition of global max? So f attains so f is on AB to R, and f attains a global max at some point x naught if f of x naught is bigger than or equal to f of x, and this is true for all x in the domain. So in other words, if the sup norm of f is actually equal to f of x naught, okay? And similarly, f attains a global min at a point if, let's put this in here, if f of x naught is less than or equal to all of the points, right? So say I have a function that's continuous and that's a graph of my function f and it's on a AB, then my local max would occur here and here and here. Or local max attained at and then local min attained at, well, that's a local min, so it could be, T naught, that's a local min, T1, that's a local min, T2, and that's a local min, T3, right? Okay, so what we're saying is for the extreme value theorem is if you have a function that's continuous, it has to attain its extrema. So there has to be, so the sup is really a max. That's maybe a good way to summarize it. So sup of f over AB is actually max of f. And the same thing with inf. Okay. And the reason why it's true, of course, is if you're continuous function on a compact set, that means that the image is compact, right? The continuous image of a compact set is compact. So the image is compact. That means that the image is closed and bounded. Closed and bounded subset in R will have the sup and the inf actually be the max of the min. So that's the extreme value theorem. And we're going to use this in our proof of roles theorem, okay? So first thing, this is just an overview or summary of the proof of roles theorem. First thing is we're going to say, hey, without loss of generality, f is constant. Why can we assume f is constant? Non-constant. If f is constant, then certainly there's a point where f prime is equal to 0 because f prime is going to be equal to 0 at every point in the function, right? If the function is constant, then the derivative is equal to 0 everywhere, right? So the interesting case is when f is non-constant. And then step 2, by the extreme value theorem, because f is continuous on this compact domain, f has to attain a max and a min at some point, maybe x0, x1, right? The max and the min aren't going to be on the endpoints because f is non-constant. And so then we'll just be able to say that, at a max, this theorem here tells us that the derivative has to be equal to 0, so we're done. Right, so this is by our last theorem. Okay, so let's go ahead and write up the proof. Here's our proof. So the proof is, or here is a proof. So the proof. So first, or wait, did I do hypothesis claim? Let's go ahead and do our formal setup. So hypothesis is that f goes from AB to R. F is continuous on AB. F is differentiable on the interior. F of A, or f of B, is equal to f of A. And the claim is that there exists x0 in AB such that f prime of x0 is equal to 0. And so now for the proof, we first start off by saying without loss of generality, f is non-constant, right? Because if f is constant, then the claim is already true because the derivative of f would be equal to 0 on the entire interval, open interval. Okay, so now we're in a situation where here's A, here's B, and f of A is equal to f of B, but our function is non-constant. Okay, so the next thing we're going to do is, since f is continuous on AB, the extreme value theorem implies there exists x0 in AB such that f of x0 is equal to the max of the set of f of x such that x is in between A and B. Okay? Now, it suffices to show, or by our last lemma, by our last theorem, it suffices to show that x0 actually belongs to the interior, right? Because our last lemma said if your function is differentiable on an interval and if f attains a max at some point in that interval, then f prime is equal to 0 at that max, right? So by our last theorem, it suffices to show that x0 is not equal to A and x0 is not equal to B. Okay, so what would happen if x0 is equal to A? Well, now, could it be the case that our max occurs here? Well, now that I'm thinking about it, yeah, sure. What if your function looks like that? Then your max actually is at A and it's at B, right? So let's go back and adjust our proof, because if we're in this scenario here, remember there has to be some point where the function attains its minimum. So then we would say, hey, use this minimum, use that point x0 to show the existence of a point whose derivative is equal to 0. So let's go back and adjust our proof and say, the EVT implies there exists an x naught and a t naught. Okay, such that f of x naught is the max and f of t naught is the min. Okay, and then by our theorem, it suffices to show that x is in here or t naught is in here. Okay, so then we'll say suppose x is either a or b, right? Then if x is either a or b or x naught, right? If x naught is a or b, then f of a equals f of b is equal to the max of f of x, where x is in our domain here, right? So since f is non-constant, that means that t naught has to be in here, since f is non-constant, right? Because that implies that f of t naught is strictly less than f of x naught, right? So t naught is in here as desired, right? So we basically have two cases. Either x naught is in the interval, in which case we're done, apply the last theorem, or if x naught is one of the endpoints, then that means that t naught has to be in the interval, the open interval, so we're done, okay? All right, so that is the proof of Rolle's theorem, right? And we're basically using the theorem that we proved before to say that if you have a function that's differentiable and that function attains a max or a min at a point, then the derivative at that point has to be equal to 0, right? So now let's look at the mean value theorem. That's supposedly the name of this lecture. But the mean value theorem, the MVT, this is super important. And it's basically a generalization of Rolle's theorem. So the mean value theorem has the same setup. You have a function that's defined on a closed interval AB. The function is continuous on its domain and differentiable on the interior of its domain. The claim is that there exists some point in the interior of its domain whose derivative is equal to f of b minus f of a over b minus a. So this is also known as the average rate of change of our function over the interval AB, right? Because it's what's the change from as you move from A to B divided by the distance from A to B, okay? So if we look at the geometric interpretation of the mean value theorem, we can see that, again, we have a function that's defined on this interval AB. It's differentiable on the open set AB. And we're basically saying that there's some point x whose derivative is equal to f of b minus f of a over b minus a. This just so happens to be the slope of the secant line through this point here, b comma f of b and a comma f of b. So if I look at the line through these points, the slope, right, is the change in f over the change in x. So f of b minus f of a over b minus a. So we're saying that somewhere there has to be a point that has the same slope. And in this case here, this drawing here, there are actually 3 points, right? So the slope of the tangent line has to be the same as the slope of the secant line. There has to exist some point where the slope of the tangent line is the same as the slope of the secant line. So the summary of the proof is you're supposed to consider First of all, consider that secant line, right? And then apply Rolle's theorem to the function minus the secant line. Because if we're looking at the function minus the secant line, we're basically looking at this difference, right? And the difference will be 0 at A and will be 0 at B. So we'll end up with a function that is still continuous, that is still differentiable on AB, but the values at the endpoints will be 0. Make sense? So we can apply Rolle's theorem to the difference between the function and the line, that secant line, through those 2 points. Okay? So let's go ahead and, do our proof here. So the setup is that f is continuous on AB and it's differentiable on the open interval. And the claim is that there's some point in the interior where the derivative of f is equal to, that's the slope of that secant line. So for the proof, as we said, we're going to consider L of x. L of x is the secant line through the points A, f of A, and B, comma, f of B. So secant versus tangent, just in case you don't know this. Secant, tangent. So tangent means you're going in the same direction, right? You're together. Secant is to cut. The Latin root of secant, I think, is the same as like bisect. So that SEC, secede, you know, if you have a country and parts of it are seceding, they're pulling away. So to cut, SEC, cuts. So the secant line cuts the function. The tangent line is really close to the function. The tangent line hugs the function, stays close to it. The secant line cuts the function, okay? So let L of x be the secant line through these 2 points, okay? So now let's find the formula for L of x. Now the equation for a line would be y minus y naught is m times x minus x naught, right? So it'd be y equals this time plus y naught. So that's the equation of a line. So I want my y to actually be L of x. And my slope is going to be, I need the equation of a line through 2 points. So the slope is going to be f of b minus f of a over b minus a. And then I can use as my point x naught, y naught. I can just use, a, f of a, okay? So this is my equation of L of x. And I'll say, then consider g of x defined to be f of x minus L of x. Notice that g satisfies the hypotheses of Rolle's theorem. How do we know it satisfies the hypotheses of Rolle's theorem? Well, for Rolle's theorem, we need the function to be continuous on AB, the closed interval. That's continuous. A line is always continuous, so G is going to be continuous. We need it to be differentiable in the open interval. That's differentiable by hypothesis. A line is differentiable everywhere, so the difference will also be differentiable on the open interval AB. And then lastly, we need G of A to be equal to G of B. So that's the question is f of A the same as L of A? And the answer is yes, because we're looking at the line L of x is the line through these 2 points. So L of A is constructed to be the same as F of A. And L of B is constructed to be the same as F of B, right? So this means there exists some point x naught in AB such that G prime of x naught is equal to 0. But that means that in order for G prime to be equal to 0, that means that F prime is equal to L prime, right? L prime is just going to be this slope here. So we get the claim. So I'll say since G prime of x is equal to F prime of x minus F of B minus F of A over B minus A, the result follows. Okay. So that's the mean value theorem. And the mean value theorem has lots of applications, and it allows us to do estimates. The mean value theorem is pretty awesome. And because it connects the values of the function at the endpoints to, it gives us the values, it gives us information about the derivative, right? The derivative of the function on the inside related to the values of the function at the endpoints. Okay, so let's look here. This fact is one of the consequences of the mean value theorem. And we're very comfortable with this fact. This fact says that if the function is differentiable and its derivative is identically equal to 0, that function has to be constant, right? So let's go ahead and prove this, and we can prove it using the mean value theorem. So let's go ahead and write our hypothesis. Hypothesis would be, suppose you have a function f, it's defined on some domain AB, and f prime of x, or let's say f, let's say here, so f is on some, so say f is on some subset. Let me actually check to see exactly the wording that Ross uses, because I want to follow the text. Let's see here. Yeah, so f has it, Ross has f being defined on the open interval AB, and f prime is equal to x for all x in our domain. And then the claim is that f is constant on AB, okay? So for the proof, let's just do a proof by contradiction. So suppose not. So if f is not constant, right, so here's A and here's B. If f is not constant, then that means that there have to be 2 points where f disagrees. So then there exists x naught, x1 in AB, 2 distinct points. X naught is not equal to x1, and f of x naught is not equal to f of x1. Okay? So if here's x naught and here's x1. Now, I cannot apply the mean value theorem directly because for the mean value theorem, your function has to be continuous on the closed set. So what I'm going to do is I'm going to say there has to be some say this is alpha and some beta, right? So first of all, without loss of generality, say x naught is less than x1. So whichever one is to the left, we'll call that x naught, right? You have 2 points, they're distinct by order properties of the real set of real numbers. One of them has to be less than the other. Call the smaller one x naught. Okay? So now there exists alpha and beta such that alpha is less than A, less than x naught, less than x1, less than beta, less than B. Then apply the mean value theorem to F going from alpha beta to R, right? F restricted to that compact domain. So we see that there exists some C, or say theta, in between x0 and x1, or in between alpha beta, such that f prime of theta is going to be equal to, oh wait, I think maybe we can just use x0 to x1. Yeah. So we don't need to do alpha beta. So let's see here. So we'll say then apply the mean value theorem to F, and now I want to just say F goes from x1 to x2, x0 to x1. Okay, so we see that there exists a theta in between x0 and x1 such that f prime of theta is going to be equal to f of x1 minus f of x0 over x1 minus x0. Now this is not equal to 0, right? But on the other hand, it's supposed to be equal to 0 since f prime is supposed to be equal to 0 for all x in AB. So this one is by hypothesis, and this one is by this. Okay, so your contradiction and that implies the result, or that implies the claim, the desired claim. All right. Okay, so now we can freely use the fact that if the derivative is identically equal to 0, then the function has to be constant. Let's see another fact. Another fact is that antiderivatives are unique up to a constant. And this is great because this means once we find an antiderivative for a function, then we know any other function, any other antiderivative has to be the same plus a constant, right? So this really saves us time and energy when we're trying to integrate functions. Okay, so let's look at the statement here. This fact says that suppose you have differentiable functions f and g, and the derivatives are equal to each other, right, on the entire domain, then there has to be a constant such that f is really g plus c, okay? Now, for the proof, I'm not even going to write this all the way out, so the sketch of the proof will be as follows. We're going to say, basically, look at the function f minus g. So consider h, which is defined to be f minus g, right? Then h is going to be differentiable, right? So h prime is identically equal to 0 on AB. So by our last fact, h is constant, right? So h of x is equal to some constant, so let's just say there exists a C in R such that h of x is equal to C for all x in AB, right? And then, well, h is really equal to f of x minus g of x, right? So f of x is equal to g of x plus c for all x in AB, right? So that's essentially the proof, and I think that's more than a sketch. I think I actually laid it all out there. But okay, so there we go. That proves that. So antiderivatives are unique. And let's look at this one. This is talking about the shape of the graph. So we can use the mean value theorem to prove information about the shape of the graph of f. And just as a reminder, we talked about this earlier in the semester, but let's go back and refresh. A function is increasing. Is increasing if, let's see here, what's the definition of increasing? So f is increasing. Well, we know what it looks like if we draw the picture, right? So it's kind of like this. So that means if x1 is less than x2, then f of x1 should be less than or equal to f of x2. Okay? And decreasing is similar. So the only difference is that you're decreasing, your graph is decreasing, you're decreasing if, okay, here's x1 and here's x2. So f of x1 should be bigger than or equal to f of x2, okay? And then strictly means that you remove the possibility of equality, okay? So the corollary is that if you have a function that's differentiable, then if your derivative is always positive, your function is strictly increasing. If your derivative is always negative, then your function is strictly decreasing. Derivative is greater than or equal to 0, the function is increasing. If it's less than or equal to 0, the function is decreasing. Okay, so let's just do a quick sketch. So hypothesis, f goes from a, b to r. F prime of x is bigger than 0 for all x in a, b. Okay, and the claim is that f is strictly increasing. So so let's see here. So if you have x1 less than x2, does that imply that f of x1 is less than f of x2? That's the question. Well, let's see here. So say you have, here's x1 and here's x2. Now, there exists a theta in between x1 and x2 such that f prime of theta is going to be f of x2 minus f of x1 over x2 minus x1, right? Since f prime has to be greater than 0, that means this has to be greater than 0. The denominator is going to be positive, so that means that the numerator also has to be positive. So this is going to imply that f of x2 minus f of x1 over x2 minus x1 is greater than 0. That's by hypothesis. And this is going to imply that f of x2 is minus f of x1 is bigger than 0. Okay? So this first implication is by the mean value theorem, right, since f is differentiable. Okay, and then the second implication is by hypothesis, our derivative is strictly greater than 0 all the time. Okay, and then the last one is just, properties of numbers. The proofs of the others are similar. So for instance, if we wanted to do this proof that f is increasing, if you now have the requirement that f prime is greater than or equal to 0, well, we would just go back and say we wanted to remove the strictly. That means we're allowing f of x1 to be less than or equal to f of x2. Okay, well now, by the mean value theorem, this part is still going to be true. There's a theta where the derivative of f at theta is equal to that difference quotient. And now by hypothesis, our hypothesis was changed to allow f prime to be greater than or equal to 0. So that means that this difference quotient is greater than or equal to 0. The denominator is positive, so the numerator is greater than or equal to 0, right? So we'll get what we want. We'll get what we want by the same rationale, okay? And then again, proving the strictly decreasing and decreasing are very similar. So I won't bore you with those details. Okay, so let's talk a little bit about the intermediate value theorem for derivatives. Let's see here. I think maybe I will postpone this for our discussion on the summary of the properties of real value functions, important properties. So I'll postpone this talk of intermediate value theorem for derivatives. Yeah, I'll postpone that talk. And so here's the last topic we'll cover. The last topic will be the derivative of an inverse. Let me just give you a sketch of what can be said about the derivative of an inverse function. So here we go. So the setup is that you have f and g as invertible. So that means invertible functions, inverse of each other. So suppose g composed with f of x is equal to x, and this is true for all x in a, b. And f and g are differentiable. And we can also put in here, just so we're quite sure that they are invertible, put that g composed with f is equal to x, and also f composed with g of x is equal to x, okay? So g and f are inverses. Okay, then watch this. If I look at the derivative of g composed with f, that's just going to be the derivative of just x, right? So on the one hand, that's going to be equal to just 1. But on the other hand, I can use the chain rule and say that'll be equal to g prime of f of x times f prime of x, okay? So this is going to be by chain rule. And this is because f and g are inverses, so it's equal to the identity. Okay, so we're going to be able to come up with a formula for our derivatives by equating these two results. Okay, so g prime of f of x times f prime of x is equal to 1. So that means g prime of f of x is 1 over f prime of x, assuming that f prime of x is not equal to 0. Okay. Now, what you'll see written in books is, suppose you have a point x comma or x naught comma y naught. Now the y naught would be f of x naught. Then we're saying g prime of y naught, because the y naught is the same as f of x naught, would be equal to 1 over f prime of x naught, right? So it's just a formulation of the relationship between the derivatives of inverses, okay? And I will leave you to look at the examples in Ross, examples 2 and 3, and Ross at the end of section 29. So just to give you a preview, one of the examples is saying to compute you know, we know about the example 2 is looking at, if f of x is equal to x to the n, and we can prove that with our basic properties of differentiation. Well, now the inverse of that, g of x, is, right, nth root of x. We can find formulas for the derivative of g, and that comes in handy. And then this example 3 is talking about inverse trig functions. So f of x is sine x. Your domain is minus pi over 2 to pi over 2. G of x, sine inverse or arc sine of x, right? So how do you compute the derivative easily? Using the formula for derivatives of inverses. Okay. All right, so that is it for this lecture. And as usual, let me know if you have any questions.